Hi, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for sleepy minds. Tonight we follow a single beam of light, what photons are, how lenses bend them, why colors appear, and how your eyes and brain turn waves into sight. No hype, just calm, clear steps. Dim the room, settle in, and let the physics of light carry you towards sleep. But before you do that, take a moment to like the video and subscribe to the channel. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world, and thank you so much for being here. Light seems simple. You flip a switch and a room glows, but under that glow is a deep idea. Light is energy that moves through space as a traveling disturbance in electric and magnetic fields. You don't need the math to feel the shape of it. Imagine a smooth, repeating ripple that carries energy forward without moving any actual stuff along with it. That ripple can cross the emptiness between the sun and earth, which is why sunlight warms your face even though space is almost a vacuum. This moving field is what we call an electromagnetic wave. Long before we used fancy words, people noticed that light bounces, bends, and splits into colors. Much later, scientists learned it shares a family with radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. The differences are only in the spacing of the ripples and how fast those ripples wiggle. The tighter the wiggle, the more energetic the light. The colors we see, red through violet, live in a narrow slice humans evolved to use because our star shines most strongly there, and our atmosphere lets that slice through. But there's a twist. Sometimes light behaves like a shower of tiny packets, each carrying a fixed chunk of energy. We call those packets photons. Think of a photon as a single click of light, a tiny messenger that can bump an electron, trigger a chemical reaction, or set off a signal in the cells of your eye. Is light a wave or a particle? The best answer is that it shows both kinds of behavior, depending on how you test it. Waves explain interference and diffraction, those soft striped patterns you get when light passes through narrow openings. Particles explain how matter absorbs light in discrete steps, and why faint light arrives as individual flashes on a sensitive camera. In everyday life, you don't need to pick a side. When you dim the lamp, you are simply letting fewer photons per second fly into the room. When you blur your eyes and see a soft halo around a point, you are seeing the wave sides spread and overlap. Another key idea is speed. In empty space, all light, every color, every kind, moves at the same top speed. In air, glass, or water, it slows a little, and that slowing is why light bends when it crosses from one material into another. Because light carries energy and momentum, it can push on objects, however gently. Sunlight can nudge dust in space, and powerful lasers can trap tiny beads. Step back and the picture is simple and beautiful. Light is the language the universe uses to move energy and information, from the birth of stars to the screen you're looking at right now. Our eyes, our devices, and our stories are built around that language, even if most days we don't think about it at all. To understand why some light warms your skin and some gives you a sunburn, it helps to meet three friendly dials: wavelength, frequency, and energy. Wavelength is the distance from one crest of the light wave to the next. If you could freeze a beam and lay a ruler along it, red light would show long, lazy spacing, while blue light would show tighter, shorter spacing. Frequency tells you how many crests pass a point each second. When wavelength is long, frequency is low. When wavelength is short, frequency is high. They are two sides of the same coin. Energy rides with frequency. Higher frequency means each photon carries more punch. Lower frequency means a softer tap per photon. In the visible range, red photons are the gentle ones, and violet photons are the energetic ones. Slide beyond visible, and you meet infrared, with longer wavelengths that we feel as heat. Longer still are microwaves, and then radio waves, which carry signals around the planet. Go the other way, past violet, and you hit ultraviolet, energetic enough to damage skin cells, then X-rays and gamma rays, which can slice through tissue and even thick metal depending on their energy. All of these are the same phenomenon, the same kind of electromagnetic wave, just tuned to different settings. One more dial matters in daily life: intensity. Intensity is how many photons arrive each second in each patch of space. A dim candle and the sun are made of the same colors, but the sun floods you with many more photons of every kind. That is why a quick look at the sun can harm your eyes, even though its visible colors are familiar. When light travels through different materials, its speed changes, and so does its effective wavelength inside the material, while its frequency stays the same. That constant frequency acts like a name tag the wave keeps from layer to layer. Materials respond differently to different frequencies. Some glass passes visible light but blocks ultraviolet. Some plastics absorb infrared strongly and feel warm under a lamp. Dark cloth absorbs a wide range of wavelengths and heats up in sunlight. A white surface reflects many wavelengths and stays cooler. Living things make clever use of these dials. Leaves look green because pigments absorb red and blue more strongly, using that energy in chemical reactions, and reflect green back to you. Your skin warms in sunlight because water and other molecules inside you absorb parts of the infrared. Night vision cameras see in the long-wave infrared your eyes ignore. Microwave ovens target a specific frequency absorbed by water and fats, jostling them and heating food from the inside out. In cameras and screens, we pick a small set of wavelengths and mix them to create the illusion of countless colors. Behind every scene you admire is this simple tuning system. Adjust wavelength, frequency, energy, and intensity, and the same physical wave tells very different stories: a cool shadow, a rosy dawn, a safe X-ray, or a warning label that says "Do not stare into beam." Light begins in motion. Heat something and its atoms jiggle. Faster jiggling means more bumps between charges, and moving charges create light. That is thermal radiation, and it is why a stove coil glows dull red before your eyes feel the heat, and why the sun, a giant ball of hot gas, shines across space. Hotter objects glow bluer because they give off more high-energy photons. Cooler ones glow redder. The sun's surface is hot enough that its strongest output lines up with the colors our eyes evolved to use. A candle, much cooler, leans toward warm orange and red. But thermal glow is only one path. Atoms and molecules can also absorb energy in little steps and then give it back as light when electrons fall from a higher step to a lower one. Each element has its own ladder of steps, so it emits at specific colors like fingerprints. That is why streetlights used to have their own personalities. Low-pressure sodium lamps cast a pure yellow, while mercury vapor lights lean toward blue-green. This line emission is how we read the chemistry of stars and nebulae from far away, and how neon signs paint letters after electrons pass through gas and bump those atoms into glowing states. Modern lighting uses semiconductors to make light more efficiently. In a light-emitting diode, or LED, electrons cross a tiny gap inside a crystal. When they drop into empty spots on the other side, they release energy as a photon. By choosing the material and the size of the gap, engineers set the color. Many white LEDs start with a blue or ultraviolet chip and a coating that converts some of that light into a spread of other wavelengths, which your eye blends into white. LEDs waste far less energy as heat than old bulbs. They switch instantly, and they can be dimmed and controlled with little electronics. Lasers are a special case. Most light scatters in many directions and phases, but a laser is coherent. Its photons march in step and in one narrow color. Inside a laser, a medium such as a crystal or gas is pumped with energy until more atoms sit in an excited state than in the ground state. One passing photon triggers many identical releases, like a stadium wave, and the device shapes that wave into a tight, straight beam. Coherence lets lasers carry information down hair-thin fibers, cut metal cleanly, scan barcodes across a store, and point precisely for measurements. Not all light sources are designed, some are surprises. Lightning makes a short, brilliant flash as electric charge tears through air and excites molecules. The aurora paints the sky when charged particles from space rattle oxygen and nitrogen in the upper atmosphere. Fireflies and deep-sea creatures use bioluminescence, chemical reactions that make photons without much heat. Fluorescent paints soak up invisible ultraviolet and give back visible glow. In all cases, the rule is the same. Shake charges, or let excited states relax, and light appears. By learning the paths from energy to photon, we build tools that fit our needs. Streetlights that save power, screens that show rich color, fiber lines that carry the world's conversations, and sensors that can see what our eyes cannot. When a beam of light reaches an object, four things compete for its future: absorption, reflection, scattering, and transmission. Absorption is when the object's electrons take the photon's energy and keep it. The energy often turns into heat or drives a chemical change. A black asphalt road absorbs across many wavelengths and warms quickly. Your skin absorbs ultraviolet and can be damaged if there is too much. Leaves absorb red and blue to power photosynthesis. Reflection is when light bounces away. A smooth mirror reflects in a tidy way, sending incoming beams out at precise angles. That's why you see clear images in a lake on a still day. A rough surface reflects in many directions, which is called diffuse reflection. That's why paper looks bright from any angle, even though it is not a mirror. Transmission is when light passes through. Clear glass transmits visible wavelengths well, but blocks much of the ultraviolet, which is handy for windows. Water transmits blue and green better than red, so deep oceans look blue because red is absorbed first. Scattering is the middle ground where light interacts and changes direction, especially inside a material or a gas. Tiny particles and molecules scatter light in ways that depend on wavelength. Our blue sky is a perfect example. Air molecules scatter short wavelengths more than long ones, sending blue light down to your eyes from every direction, while red passes through more directly. At sunset, the path through the atmosphere is long, blues are scattered away, and the remaining direct light is rich in red and orange. Larger particles, like haze or fog droplets, scatter all visible colors more evenly, which makes distant scenes look washed out and white. Materials mix these processes in countless proportions, and that mix is what we perceive as appearance. Glossy paint reflects in a narrow angle and looks shiny because you see a highlight. Matte paint scatters light broadly, hiding scratches and fingerprints. Frosted glass transmits but also scatters, blurring shapes. Snow is full of ice crystals that reflect and refract millions of times. Each tiny interface scatters a little, the whole pile adds up, and snow looks brilliantly white even though ice is clear. Metals reflect so well because their electrons move easily, pushing back against the incoming wave. Pigments and dyes look colored because their molecules absorb certain bands strongly and let others escape to your eye. Even the way a surface is made changes light's fate. A brushed metal has aligned micro scratches that stretch highlights. A polished lens wastes less light at its edges. A tiny texture on a smartphone screen cuts glare without killing crispness. In architecture and film, designers play with these effects to guide mood. Soft, warm, and diffuse for comfort, or crisp and specular for a modern bite. In safety, we use retro-reflective materials filled with glass beads or prisms that throw light back toward its source so road signs pop at night. The world you see is not only about light sources, it is also about the billions of decisions matter makes every moment. Keep, bend, borrow, or bounce. Two simple behaviors create much of the magic you notice every day: reflection and refraction. Reflection follows an easy rule: the angle in equals the angle out. That is why a mirror flips left-right, but not top-bottom. It is also why periscopes work, and why a billiards player can predict a bank shot. But most surfaces are not perfect mirrors, so their microbumps send light in many directions, softening glare. Refraction is bending that happens when light crosses from one material into another, like air into water or air into glass. In a new material, light slows down by a certain factor called the refractive index. The change in speed tilts the wavefront, the way a marching band turns when one end of the line hits thick mud first. If light goes from slow to fast, say glass back into air, it bends away from the normal line that is perpendicular to the surface. That bending depends on the materials and on the incoming angle. Although the formal law has math, you can feel it with a simple picture. Part of the wave enters first, part later, and the wave swivels as it adjusts. This is why a straw in a glass looks broken at the waterline, why pools look shallower than they are, and why a mirage shimmers above hot pavement when warm air near the ground changes refractive index quickly with height. Bending creates tools. A prism splits white light into a rainbow because different wavelengths slow by slightly different amounts. Blue bends a little more than red, so the colors spread. Eyeglasses and camera lenses use carefully shaped glass to steer rays to a focus. A convex lens gathers rays to a point. A concave lens spreads them apart. By combining shapes and materials, designers correct blurs and color spreads to make sharp images on your retina or on a sensor. There is also a threshold effect called total internal reflection. If light inside a denser material hits the boundary to a less dense material at a shallow enough angle, it can't get out. Instead, it reflects back in as if the boundary were a mirror. This trick is the heart of fiber optics. A glass fiber has a slightly denser core and a less dense cladding. Light injected at the right angles bounces down the core like a polished hallway, traveling kilometers with only small losses. We use this to send phone calls, movies, and data across continents at near light speed. Nature uses the same effect in raindrops to make rainbows, and in some gemstones to create fire and sparkle. Refraction also lets us make lenses that shrink or magnify the world. A magnifying glass collects rays from a small object and spreads them across more of your retina, so details pop. A projector does the reverse, throwing a small bright image onto a large screen. In cameras, a stack of lenses moves to keep the focused plane on the sensor, whether you are shooting a mountain or a flower. Even your own eye relies on refraction. The cornea does most of the bending, the lens fine-tunes it, and the fluid in between provides the right optical environment. When focusing goes wrong, glasses simply add or subtract a little bending power to bring images back into crisp alignment. In short, by bouncing and bending light in controlled ways, we turn a physical ripple into tools that help us see, communicate, measure, and create. A lens is a shaped piece of transparent material that persuades light to change direction gently, so rays that once spread out can meet again at a point. The simplest picture is a convex lens bringing parallel rays to a focus and a concave lens sending rays outward, but in practice, lenses come in carefully chosen stacks that cancel common flaws. Real glass bends different colors by slightly different amounts, so a single lens spreads white into fringes. Designers pair glasses with different properties to tame that color fringing and keep edges crisp. The distance from a lens to its sharp focus for distant objects is the focal length. Shorter focal lengths give wide views that take in a room. Longer ones narrow the view and bring far mountains close. The aperture is the opening that lets light through. Make it wide and lots of light reaches the sensor or film, which is useful in dim scenes. Make it small and you gain depth of field, the range that looks acceptably sharp from front to back. This depth control is the quiet poetry behind portraits with soft backgrounds and landscapes where every rock and cloud looks etched. A camera balances three partners: aperture, shutter time, and sensor sensitivity to reach the same brightness with different looks. A fast shutter freezes motion but needs more light. A higher sensitivity brightens the scene but adds grain. A wide aperture keeps motion blur at bay and creamy backgrounds, at the cost of narrow focus planes that demand steady hands and careful breathing. Autofocus measures contrast or phase differences to move the lens until edges pop. Image stabilization shifts parts of the optics or the sensor to cancel tiny shakes so longer exposures stay sharp. Microscopes and telescopes are lens stories told at opposite scales. A microscope's job is to turn a tiny near field into a large, comfortable image for your eye. It stacks objectives and eyepieces to gather light from a small patch and spread it across your retina. It battles a fundamental limit. When light passes through small openings, it spreads, and that spreading sets the finest detail you can see, even with perfectly polished glass. That is why clean lenses, bright, steady illumination, and short wavelengths, blue light, help reveal fine features. Telescopes gather aperture rather than magnification first. A big mirror or lens collects more photons from faint galaxies and improves resolution because a larger opening narrows the wave's spread. Most modern giants use mirrors because heavy lenses sag. A mirror can be supported from behind, polished to nanometer smoothness, and coated to reflect most of the light that strikes. Binoculars fold long light paths into short tubes with prisms, flip images right side up, and match each barrel to each eye, so your brain fuses two slightly offset views into depth. Eyeglasses are the oldest quiet miracle of applied optics. If your eye focuses in front of the retina, nearsighted, a concave lens spreads rays a little before they enter. If your eye focuses behind the retina, farsighted, a convex lens begins the focusing for you. Cylindrical lenses correct astigmatism, a football-shaped cornea that bends light unevenly in different directions. Progressives blend powers smoothly for near and far work without a visible line. Coatings reduce stray reflections so more light reaches your eye and less bounces between surfaces to wash contrast. Screens and projectors are lenses in reverse. A small bright image passes through optics that spread it large on a wall. The sharpness depends on how precisely those optics keep different colors in the same place and how flat the focus plane is across the whole picture. Even everyday devices hide optics. A phone camera packs multiple molded elements, aspheric surfaces that act like complex shapes without heavy glass, and tiny actuators that move fractions of a millimeter with grace. A VR headset places short focal length lenses near your eyes to let you focus comfortably on a screen that is physically close. Software counterbends the image so it looks natural after the lenses warp it. Wherever you look, lenses are turning the wave's gentle bend into human comfort, making text legible, faces clear, microbes visible, the moon feel near, and the night city clean and bright without glare. Light behaves like a wave when paths are small enough to matter, and waves do what ripples on a pond do when they meet, they interfere. Where crest meets crest, brightness grows. Where crest meets trough, brightness dims or disappears. This simple rule builds subtle wonders. Shine light through two narrow slits, and you don't get two bright bars. You get a pattern of bright and dark stripes because light that traveled the extra distance to reach one point is slightly out of step with light from the other slit. The extra distance might be one full wavelength, bright again, or half a wavelength, dark, or something in between. This double-slit experiment is not a party trick. It is a window into how all waves share space. In the thin film of a soap bubble, some light reflects from the outer surface. Some enters, reflects from the inner surface, and emerges. The two paths differ by a tiny distance. For some colors at a given film thickness, the paths recombine in step and blaze. For others, they cancel, so you see shifting bands of color as the bubble thins and flows. Oil slicks on wet asphalt, anti-reflection coatings on lenses, the subtle colors on a beetle's wing. These are interference paintings made by nanometer-scale layers. Diffraction is interference caused by edges and openings. Anytime light passes a small aperture or brushes a sharp edge, it spreads into a pattern rather than marching straight. The smaller the opening relative to the wavelength, the wider the spread. That spread puts a hard limit on image sharpness. Even the best lens turns a pinpoint star into a tiny bullseye pattern called an airy disk with soft rings around it. A larger aperture produces a smaller airy disk, which is why big telescopes and camera lenses can resolve fine detail if the air stays steady. The focusing scale of a microscope is capped by the wavelength and the numerical aperture of its optics. You can't cheat the physics, though clever tricks like immersion oil can gather wider angles and pull a bit more detail. Diffraction gratings, surfaces ruled with thousands of narrow lines, turn white light into spectra by sending each wavelength off at a slightly different angle. A CD's tracks act like a grating and throw rainbow shards across your wall. Modern spectrometers use precise gratings to read the chemical fingerprints of light from stars or lab lamps. Lasers reveal interference more blatantly because they are coherent. Shine a laser on a wall and you may see a grainy speckle pattern, bright and dark grains formed by interference of the many paths scattered from tiny bumps. Interferometers split a beam, send halves along different paths, and bring them back together. If one path changes by even a fraction of a wavelength, because a mirror moved, a gas warmed, or a gravitational wave whispered through space, the pattern shifts. This sensitivity makes interferometers supreme rulers for metrology, from measuring chips on a wafer to checking the flatness of telescope mirrors to listening for cosmic ripples. In everyday life, diffraction explains why small camera apertures can go too far, stop down to gain depth of field, and eventually the spreading blur softens the whole image. It explains why your shadow's edges are never perfectly crisp, why sound sneaks around doorways while light mostly doesn't, and why radio antennas have shapes and sizes that match their wavelengths so they can beam signals instead of spraying them. Interference and diffraction are not exotic. They are the fair, predictable ways that waves share a world. Learn their patterns and you gain both artistry, control over color and sheen, and engineering control, limits you can plan around and sometimes turn into useful signals. A light wave is an electromagnetic ripple with an orientation. As it moves forward, its electric field wiggles in a direction that can be vertical, horizontal, or anything in between. Ordinary light is a mix of all orientations. We call that unpolarized. When most waves share the same orientation, the light is polarized. Polarization sounds abstract, but your sunglasses use it every sunny day. When light reflects from flat non-metal surfaces, water, car hoods, wet roads, Certain orientations dominate at a specific angle, the Brewster angle. A polarizing filter is made of long-chain molecules aligned like a picket fence. It absorbs the component of the electric field parallel to those chains and passes the perpendicular component. If glare is horizontally polarized, a filter with vertical transmission will clip that glare and leave the richer scene intact, which is why polarized sunglasses make lakes darker and clouds pop. Rotate the glasses and the effect grows and shrinks because you're lining that molecular fence with or against the glare. The sky itself is partly polarized because sunlight scatters off air molecules. Maximum polarization happens about 90 degrees away from the sun. Some animals, like bees, can sense this pattern and use it to navigate when the sun hides. Photographers use polarizers to deepen blue skies, reduce reflections on leaves, and reveal what's beneath shallow water, though they must accept a small loss of light and sometimes uneven skies with very wide lenses. Screens exploit polarization too. Many LCDs sandwich a liquid crystal layer between two polarizers set at right angles. With no voltage, the liquid crystal twists the polarization so light slips through both filters. With voltage, the twist unwinds and the second polarizer blocks the light. Control millions of tiny cells and you control an image. Tilt your head or view some laptops from odd angles and you'll see brightness and color shift because you're changing how your eyes meet those polarizers. 3D cinema often uses polarization, projecting two images with perpendicular orientations and handing you glasses with matching filters. Each eye sees only its intended image, and your brain builds depth from the slight differences. Other theaters use time sequence shutters or color tricks, but the goal is the same. In labs and factories, polarization is a diagnostic tool. Transparent plastics under stress rotate polarization by different amounts in different directions. Place them between crossed polarizers and stress fields bloom as bright colors, letting engineers find weak points. Minerals reveal their crystal orientations under polarized microscopes. Fiber optic systems worry about polarization because fibers can favor one orientation and scramble another, affecting data rates. Radio and microwave antennas also have polarization. A vertical antenna hears vertical best, and misaligned links waste power. Even the Brewster angle has practical uses beyond sunglasses. At that angle, reflections in one polarization vanish from a clean dielectric surface, so lasers and optics are designed with coatings and angles that control which polarization is reflected or transmitted to keep internal ghosts low. The key idea is simple. In addition to brightness, color, and direction, light carries a fourth property, orientation of its wiggle, that you can filter, twist, and measure. Knowing that gives you cleaner photos, calmer eyes on water, better screens, subtler lab instruments, and a new way to notice the invisible order riding in daylight itself. Color begins as physics and ends as perception, but there's a practical middle where we mix and manage it. When you add colored light sources, you get additive mixing. Shine red and green lights together, and you see yellow. Add blue, and you approach white. Screens use tiny subpixels, red, green, and blue, packed so tightly that your eye blends them. By changing each subpixel's brightness, a display draws millions of colors. The range it can reach is its gamut. Wide gamut screens can show more vivid greens and reds than older ones because their primaries are purer. When you mix pigments, you mostly get subtractive mixing. Paints and inks absorb portions of white light and reflect the rest. Combine two, and you usually absorb more, leaving less to reflect. That's why mixing many paints tends to muddy browns. You're stacking absorption bands. Printers use CMYK, cyan, magenta, yellow, and black, because cyan absorbs red, magenta absorbs green, and yellow absorbs blue. By overlapping tiny dots, you subtract different parts of the spectrum and create the appearance of many colors. Black ink deepens shadows and saves ink when making text and dark areas. Between displays and printers lies color management, profiles that translate numbers meant for one gamut into the closest matches in another, so a sunset on your laptop doesn't turn dull on paper. Light sources have different spectra. A candle's warm glow is rich in red and poor in blue. A midday sky leans blue. A fluorescent tube can have spiky output at certain lines. A white LED often starts with a blue chip and a yellowish phosphor, filling in the middle while sometimes dipping in deep reds. These differences shape color rendering, how natural skin, food, and art appear. High CRI or high TM, 30 scores signal sources that spread their output smoothly, so many objects look right. Color temperature is a way to label a source's tint along a warm to cool line by comparing it to an ideal hot object called a blackbody. 2700 Kelvin suggests cozy tungsten-like warmth. 5000 to 6500 Kelvin suggests daylight-like coolness. Cameras and your eyes do white balance and attempt to treat a chosen neutral as truly neutral, nudging the whole scene warmer or cooler to compensate. Our visual system adapts quickly, which is why a white shirt looks white in morning sun and under a warm lamp. Your brain retunes the scene, a trick called color constancy. Screens and lights also play with HDR, high dynamic range, which is more about brightness than hue, but it changes color's impact because saturated colors pop more when you can keep highlights bright and blacks dark. Metamers are different spectral mixes that look like the same color to human eyes because they produce the same stimulation in our three kinds of cones. This is the foundation of trichromatic displays, and the reason two fabrics can match under one light and clash under another with a different spectrum. Filters and gels shape color by absorbing bands, handy in theatre and photography. Dichroic filters reflect bands instead of absorbing them, staying cool and efficient in projectors. In mixing, remember a few gentle rules. Light adds, paint subtracts, displays can show colors inks can't, and inks can print subtle pastels that some screens overpunch. Warm/cool labels are conventions tied to blackbody-like sources, and what white should be depends on your purpose, which is why cameras let you pick daylight, tungsten, shade, or roll your own. Get curious about spectra and you earn control. Food looks tastier under sources rich in red. Art deserves lamps with smooth output across the board. Night reading wants a source bright enough for letters with as little short wavelength spill as practical to keep sleep on schedule. Color is cooperation between physics, devices, and your brain. Learn the handshake and your images, rooms, and prints will feel calm and true. Your eyes are compact cameras with living parts that repair themselves and talk to a brain that edits in real time. Light first meets the cornea, a clear dome that provides most of the bending needed to focus. It passes through the pupil, an opening set by the iris, which widens in dim scenes to catch more light and narrows in bright scenes to protect and sharpen. Behind the pupil sits the lens, a flexible, transparent protein disc whose shape changes to fine-tune focus, a process called accommodation. With age, the lens stiffens, which makes near focus harder, that familiar stretch of arms before reading glasses step in. The image forms on the retina, a thin layer lining the back of the eye. The retina holds two main light sensors: rods, which are very sensitive, see in low light, and do not register color, and cones, which need more light but supply color and fine detail. Humans typically have three kinds of cones with different peak sensitivities: often labeled short, blue, medium, green, and long, red. Your sense of color is built from their combined responses, not from single red or blue pixels in the world. At the very center is the fovea, a tiny pit packed with cones where your sharpest vision lives. Away from the fovea, cones thin and rods dominate, which is why at night you often see a faint star better if you look a little to the side. There's a spot with no sensors where the optic nerve exits, the blind spot, but the brain fills it seamlessly using context. Photoreceptors don't fire like camera pixels. They change their chemical state when photons hit, modulating signals that bipolar and ganglion cells encode. The optic nerve carries these encoded differences to the brain, where layers of processing build edges, motion, depth, and color constancy. The retina already performs compression. It is more sensitive to change than to steady fields, which saves bandwidth and emphasizes what matters. The eye and brain can handle a huge dynamic range by adapting. Step from shade into sun, and you're briefly dazzled as pigments and pupil catch up. Linger, and the scene normalizes. In dim rooms, rods take over. The world desaturates, and your sensitivity to blue-green rises compared to red, a shift called the Purkinje effect, which is why red instrument lights preserve night vision. Saccades, tiny rapid jumps, keep your scene fresh. Between jumps, the brain suppresses blur, so your world doesn't smear even though your eyes are in constant motion. Depth comes from a fusion of cues. The slight difference between your two eyes, binocular disparity, focus changes, relative size, perspective lines, occlusion, and motion parallax as you sway. The pupil reflex and blink protect and lubricate. Tear film smooths the cornea. The choroid supplies nutrients. Supporting cells recycle photopigments so receptors recover. Color vision varies across people. Some have shifted cone sensitivities. Some lack one class of cone, common red-green deficiencies, which changes how hues separate but not how rich the world feels. A few have an extra cone class and may see subtle distinctions others miss. After images, like a green ghost after staring at a red square, arise because cones adapt to steady input and then briefly over or under respond when the scene changes. Color constancy is your brain's habit of estimating the light source and discounting it, so a white shirt stays white under many lamps. Cameras try to imitate this with white balance. Blue-rich light at night can delay melatonin release and shift sleep timing. Not because blue is evil, but because your body clock listens to a special set of cells that report overall blue cyan content as daytime. Dim, warmer light and screens set to lower output in the evening give your clock clearer signals. The eye is not a passive sensor sending a raw feed. It is an active, adaptive front end for a prediction machine. It balances resolution with sensitivity, speed with stability, color with brightness, and hands the brain a stream the brain edits into the steady, detailed, colorful world you trust every time you open your eyes. A modern camera is a light meter with a memory. Instead of film, most use a CMOS sensor, a grid of tiny light buckets called pixels that convert incoming photons into charge. Each pixel doesn't see color by itself. A colored Bayer filter, or similar pattern, lays red, green, and blue microfilters over neighboring pixels, and software later interpolates them into full-color pixels in a process called demosayasing. Above the grid, microlenses funnel stray photons down into each bucket so fewer are wasted, and an IR cut filter blocks infrared that would otherwise skew colors. Sensitivity, what your camera labels ISO, doesn't make the sensor catch more photons. It amplifies the electrical signal those photons created. Amplify enough, and you also lift noise. random variations from electronics, dark current, and the quantum randomness of photon arrival itself. Dim scenes show noise because few photons arrive. Bright scenes look smoother because statistics average out. Dynamic range is the span from deep shadow to bright highlight. The sensor can record before shadows drown in noise or highlights clip to paper white. Big pixels, or stacked exposures, help, as do clever readout circuits that measure charge with less hiss. Many phones now shoot several frames at different exposures and blend them into HDR, so a sky keeps detail while faces stay clear. Some even split a single exposure into multiple gains per pixel, dual conversion gain, to protect highlights and shadows at once. Rolling shutter scans rows of pixels in microsequence. Fast subjects can skew or propeller blades can bend. Global shutter grabs the whole frame at once but is trickier to design. You see it in high-end or specialty sensors. Autofocus used to hunt contrast, moving the lens until edges got strongest. Now phase detect pixels baked into the sensor compare two views to tell the lens which way and how far to go, locking quickly even in dim light. Inside every camera is a tiny lab called the Image Signal Processor, ISP. It subtracts fixed pattern noise, corrects lens shading, vignetting, fixes color shifts from wide-angle rays, balances white, demosaics, reduces noise while trying not to smear texture, sharpens edges just enough, and applies a tone curve that makes midtones pleasant instead of flat. Computational photography pushes this further, aligning and stacking multiple frames to reduce noise and boost detail, simulating shallow depth by separating subject from background, combining short exposures for highlights with long ones for shadow color, and stabilizing frames in software so handheld night shots don't wobble into mush. RAW files keep sensor data with minimal processing, letting you choose white balance, noise reduction, and tone later. JPEG/HEIC bake choices in, but keep files small. Histograms are simple truth tellers, a graph of how many pixels sit at each brightness. If they're crushed at the right edge, you've clipped highlights. If bunched at the left, you're underexposed. Neutral density, ND filters, act like sunglasses for your lens so you can use wider apertures or longer shutter times in bright light. Polarizers cut glare and enrich skies at the cost of about 1 to 2 stops of light. The exposure triangle, aperture, shutter, ISO, is really a budget. Photons in, time open, and how hard you push the amplifier. Longer shutters collect more light but invite blur unless the scene is still or the camera is stabilized. Wider apertures brighten and blur backgrounds but narrow the slice of distance that's sharp. Higher ISO fights darkness but raises noise and can reduce dynamic range. Phone cameras squeeze miracles from tiny sensors using multi-frame fusion, super resolution from microshifts, and portrait background blur estimated by depth maps or neural networks. Big sensor cameras start with more photons and often win on texture and tonal grace. In every case, you're steering the same physics. Catch as many honest photons as you can, keep them in order, decide how to tell their story, and let a quiet chorus of math clean the window without scraping away the view. A display's job is to paint controlled light toward your eyes. LCDs do it with a bright backlight filtered by liquid crystals and polarizers. The crystals twist polarization under voltage so each pixel's red, green and blue subcells pass more or less light. Different panel types trade traits. IPS keeps color and contrast more stable off-angle. A can push deeper blacks in the dark. TN is fast but shifts color quickly with angle. Local dimming carves the backlight into zones that dim behind dark scenes to raise contrast. but halos can appear around bright objects if zones are coarse. OLED flips the script. Each subpixel emits light on its own, so blacks can be nearly perfect and contrasts spectacular. Response is quick and viewing angles wide. OLED can show slight PWM flicker when dimmed. Many people never notice. And static elements risk burn-in over very long bright hours. Micro-LED aims for OLED-like black with longer life and extreme brightness, but it's young and costly. E-ink reflects ambient light like paper, sipping power for static pages. It's perfect for reading in daylight and restful at night with a lamp. Color isn't just red, green, blue. It's a space, a triangle on the spectrum. Old devices aimed for sRGB, many modern screens target display P3, richer reds, greens, or even REC. 2020 in high-end gear. If software doesn't manage color with ICC profiles, a wide gamut screen can make ordinary photos look too vivid. Good apps convert colors into the display's space, so a strawberry looks like a strawberry and not neon candy. Gamma is the curve that maps numbers to brightness. Most content assumes a familiar curve, around 2.2, so midtones look natural. HDR, high dynamic range, adds more stops of brightness headroom and often a wider color volume. Formats like HDR10, HLG, and Dolby Vision tell a display how to map bright highlights and deep shadows without crushing detail. The display's tone mapping then fits that intent into its actual peak brightness. In a sunny room, a bright screen helps. In a dark room, too bright midtones feel harsh. Good tone mapping and a sensible room light make HDR feel like window light, not glare. Refresh rate and motion handling matter for comfort. Higher rates reduce blur from eye tracking. Black frame insertion can sharpen motion at the cost of flicker. Overdrive speeds pixel transitions but can overshoot if pushed. For creators, calibration is housekeeping. Set brightness to a sane level, often 80 to 120 candelas per square meter for dim rooms, more for bright offices. Choose the right white point. D65 is the common daylight target. And load a profile so apps know the display's true behavior. If your screen is too bright, you'll edit images too dark. If it's too cool, you'll add warmth that prints as orange. Rendering pipelines juggle bit depth, 8, 10, or more bits per channel, and dithering, tiny noise that hides banding. More bits help smooth skies and gradients. Subpixel layouts, RGB, pentile, change text crispness. O, SES know these patterns and hint text accordingly. Phones lean on ambient sensors and true tone style adjustments that nudge white toward room light so pages don't look blue under warm lamps. You can disable these for color-critical work. In short, a display is a controlled lantern. Know its color space, keep it profiled, use apps that respect profiles, and choose viewing conditions that match your task. Then pictures stop arguing with the room and simply feel true. Photography is painting with light, and the brush shape matters. The size of the light source relative to the subject decides softness. A large source, as seen from the subject, delivers soft shadows and gentle skin. A small far source carves hard edges and emphasizes texture. You can make a big source by moving a lamp close and diffusing it through a softbox, umbrella, or sheer fabric, or by bouncing it off a white wall or ceiling. Direction shapes mood. Front light is forgiving but flattens. Side light reveals shape and texture. Backlight separates subject from background and can turn hair into glow if you add a small fill up front. Classic three-point lighting, key, main, fill, weaker, softer, and rim, back edge, is a clean recipe for faces. You can do it with a window as key, a reflector as fill, and a cheap clamp light as rim. Outdoors, the sky is a giant softbox on cloudy days. On sunny days, find open shade or use a simple diffuser to calm harsh noon. Golden hour, low sun, warms skin and lengthens shadows. Blue hour, post-sunset, gives calm, even backgrounds that make city lights sing. Color quality matters. Bulbs list CCT color temperature, but also look for CRI or TM30 scores. Higher means colors, especially reds, look natural. Mixing sources can cause odd skin tints. Either pick one dominant color temperature or gel your lights so they match. In camera, set white balance to the light or shoot raw and fine-tune later. Exposure is a dance between aperture, depth of field, and lens sharpness, shutter, motion blur, and ISO, noise. For portraits, a wider aperture isolates the subject. For landscapes, stop down a bit, often f/5.6 to f/11 on larger sensors. For edge-to-edge clarity, watching for diffraction at very small apertures. Metering modes, matrix/evaluative, center-weighted, spot, red light differently. If a scene fools the meter, a dark subject on bright snow, use exposure compensation or meter off a mid-tone. ETTR, exposed to the right, gives cleaner shadows by pushing exposure as high as you can without clipping highlights. It's easier on RAW files and scenes without blinking speculars. Flash freezes motion and adds shape when ambient is weak. A small speedlight off camera with a cheap wireless trigger bounced into an umbrella is a giant upgrade over direct on-camera flash. Mine sync speed so shutter curtains don't slice the frame, or use HSS to shoot wide apertures in daylight at the cost of power. Continuous LED panels are friendly for beginners because you see the look before shooting. Many allow dialable color temperature and hue. Add flags, black foam core, to control spill, reflectors, white/silver/gold, to lift shadows, and grids to narrow beams. Polarizers remove glare on water and leaves and deepen skies. ND filters let you blur waterfalls or traffic at midday without overexposing. Graduated NDS balance bright skies and dark land at the horizon. For macro, tiny movements ruin focus. Use a tripod, manual focus with focus peaking, and consider focus stacking. Several shots at different focus distances blended later. For night scenes, a tripod plus a remote or self-timer keeps stars points. Set long exposures and low ISO, and shoot during moonlit nights for gentle foreground light. Keep safety in mind. Don't look through optics at the sun without certified filters. Beware traffic when you step into the street for a reflection, and secure stands outdoors. The most important tool isn't expensive gear, it's place and time. Move your subject a meter, wait 10 minutes for softer sun, turn a face 15 degrees, switch off a harsh lamp. These free moves change everything. When light is comfortable, people are too, and your images feel like a deep breath. Light brings comfort and information, but some kinds and contexts deserve caution. Ultraviolet carries more energy per photon than visible light and can damage skin and eyes. Sunburn is inflammation from UV, hitting DNA and proteins. Years of overexposure age skin and raise cancer risk. Protect with shade, hats, and sunscreen that blocks both UVA and UVB. For eyes, look for sunglasses labeled UV 400 or equivalent. Fashion tint alone is not protection. Snow, water and sand reflect UV. In high mountains or at sea, protection matters even on cool days. Never stare at welding arcs. They pour UV that can cause photokeratitis, snow blindness, a painful sunburn of the cornea. During solar eclipses, ordinary sunglasses are not enough. Use only ISO 12312-2 certified solar viewers or an approved solar filter on optics, and remove filters only in totality if you are in the narrow path. Lasers bundle light in tight, intense beams. Even small pointers can harm if you stare into a focused spot at close range. Higher class lasers used in shows, labs, or cutting demand. Strict rules. Never aim at eyes, reflective surfaces, aircraft, or vehicles. Respect posted laser classes and barriers. Wear rated goggles matched to the laser's wavelength. Infrared feels gentle because you can't see it, but strong IR sources, industrial heaters, some lamps, can heat tissue without a blink reflex. Treat them like hot stoves. Blue-rich light at night doesn't injure the eye at normal device levels, but it can delay sleep because special retinal cells report blue cyan content to your body clock. Dimming screens at night, warming their color, and using lamps at moderate, warmer settings tell your clock evening more clearly. Flicker can cause eye strain or headaches in sensitive people. Some dimming systems, including PWM on certain LEDs and OLEDs, introduce flicker at low brightness. Choose high-quality lamps with low flicker, dim screens with settings that reduce PWM, and keep ambient light soft and stable where you work or read. HID lamps, older street lights, and UV sanitizers should be shielded. Never bypass covers. Grow lights and nail curing lamps can emit strong UV. Use gloves or skin protection, and don't stare at the arrays. Projectors are bright. Avoid looking straight into their lenses, especially with children. Kids' eyes transmit more UV than adults. Hats and sunglasses build good habits early. At work, photobiological safety standards guide lamp design. At home, basic sense covers most risk. Don't aim bright lights into faces at close range. Keep high-output LEDs diffused, and mount shop lights so they don't dazzle. For screens, comfort beats absolutism. Set brightness to match room levels. Too bright in a dark room tires eyes. Increase text size rather than leaning in, and take 20-20-20 breaks. Every 20 minutes, look 20 feet away for 20 seconds to relax focusing muscles. Finally, think about light pollution. Bright, unshielded outdoor lights wash stars, disturb wildlife, and waste energy. Use warm, fully shielded fixtures that point down, add motion sensors instead of all-night lamps, and you'll help neighbors sleep and invite the Milky Way back. Light is a tool. With small, steady habits, you keep its gifts and dodge its harms. You can make homes and workspaces calmer by treating light and color like friendly dials. Start with layers. Ambient light for overall glow, task light where eyes work, and accent light for mood. In living rooms and bedrooms, choose warmer lamps around 2700 to 3000 Kelvin. With good CRI, so skin tones and wood feel natural. Place lamps at eye level to avoid glare from ceilings and bounce light off walls for softness. In kitchens and craft spaces, slightly cooler 3500 to 4000 Kelvin keeps whites clean and counters crisp. Add under-cabinet task lighting to stop your hands from casting shadows. In home offices, match screen brightness to the room and avoid bright lights behind the display. Aim for moderate, even illumination, and if possible, daylight from the side. If you read at night and want easier sleep, keep lights warm and dim in the last hour. A small shaded lamp aimed at pages beats overhead glare. Buy bulbs by lumens, brightness, rather than watts, and favour high CRI/T M30. So fruit, clothes and faces look right. Cheap lamps can make reds dull and greens strange. For walls, matte or eggshell paints hide reflections and reduce screen glare. Glossy accents work best away from working eyes. In small spaces, cooler, lighter wall colours feel airier. In big rooms, a gentle warm tint can pull walls closer. Curtains and blinds are light valves. Sheer fabrics soften daylight. Blackout shades enforce sleep for shift workers or babies. Top-down shades give privacy while keeping sky. In the dining area, warm pendant lights above the table make food look appetizing. Avoid cold spotlights that turn soup grey. In bathrooms, flank mirrors with vertical lights at face height, or use large diffusers so shaving and makeup don't fight harsh shadows. Outdoors, pick fully shielded warm fixtures, less than or equal to 3000 Kelvin, that light paths and doorways without beaming into bedrooms or the night sky. Motion sensors and timers save energy and preserve darkness. For creating and viewing art, consistent, high CRI light matters. If you can, use 5000 Kelvin daylight lamps in a dedicated viewing corner and keep walls neutral grey so reflected colour doesn't skew your eye. For clothes and makeup, check colours in the light you'll live in. Office fluorescence, outdoor shade, or warm evening lamps, because metamers can surprise. In the kitchen, a mix of task and ambient avoids knife shadows. A small undershelf puck light often changes dinner more than a big ceiling upgrade. On screens, enable colour management in your editing apps. Set your display to the right colour space, sRGB or P3 depending on output. And keep brightness sane so prints don't come out too dark. For printing, try soft proofing and pick papers with profiles so the translation is honest. Accessibility is a colour issue too. Strong contrast ratios help everyone read. Avoid red/green only cues in charts or labels. Use patterns or icons as backups. For plants, place them where daylight fits their needs. If you add grow lights, pick spectra intended for living spaces or keep them in timed enclosures so evenings stay gentle. For photographing products or food at home, a north-facing window plus a white foam board opposite is a no-cost studio. Turn off mixed room lights to avoid colour clash. Set white balance to daylight and shoot. In every case, you don't need perfect gear. You need consistent choices. Warm where you rest, crisp where you work, high CRI everywhere faces and food matter, shields outside, and dimmers, or 2 lamp options so you can tune. Colour and light are quiet companions. When they match the task and the time of day, rooms feel like they're on your side. Step outside and light becomes a patient teacher. The daytime sky is blue because air molecules are so tiny that they scatter short wavelengths more than long ones. This Rayleigh scattering redirects blue light from the sun across the dome, so it seems to come from everywhere at once. Near sunset, sunlight must travel a longer path through the air. Along that path, the blues and violets are scattered away, leaving a beam richer in reds and oranges, which is why clouds catch fire at the edges, while the zenith hangs cool and violet. In mist and thin clouds, water droplets are much larger than molecules, so they scatter all visible wavelengths more evenly. That mere scattering makes distant mountains fade whitish and fog feel like a soft room. When rain falls under a sun behind you, millions of droplets behave as tiny prisms. Light enters, bends, reflects off the back, and bends again on exit. Because blue bends slightly more than red, the colours separate, and you see a primary rainbow at a specific angle, red outside and violet inside. If the light bounces twice inside the drops, a fainter secondary rainbow appears outside the first with colours reversed, and the band between them, Alexander's dark band, looks dimmer because fewer rays exit there. With very small droplets in thin clouds, interference builds coronas, soft pastel rings around the sun or moon. Tiny ice crystals high in cold air forge halos at about 22 degrees, sometimes with bright sundogs, parhelia, that mimic small suns to the left and right, caused by plate-like crystals drifting with flat faces. In mountain mist, if the sun is behind you and a cloud bank lies just beyond a ridge, your own shadow can sit at the center of a colored glory, tight rainbow rings formed by diffraction and backscattering from micro droplets, like a personal halo at the edge of weather. Heat can bend light too. Over hot roads, air near the surface is warmer and less dense than air above, so light curves upward. Your brain interprets the coming from above rays as reflections from a shiny surface below, and a mirage, a fake puddle, shivers into being. Over cold water, the temperature profile can flip the other way and make distant ships float eerily above the horizon. On rare, perfectly clear evenings over the ocean, the last sliver of the sun may flash green as atmospheric refraction and dispersion split and delay colours differently. The green flash is brief and gentle, not a neon explosion, and rewards patient eyes. Nature also paints with structural colour, hues created not by pigments, but by fine patterns that interfere with light. Peacock feathers, morpho butterfly wings, and some beetle shells contain layered microstructures that reflect certain wavelengths strongly and change with angle, which is why they seem to shimmer with motion. Opal's fire arises from close-packed silica spheres whose spacing diffracts light like a 3D grating. Rivers glow at night where plankton bloom because bioluminescence, a chemical reaction that releases photons, blinks to the stir of paddles or fish. On land, fireflies time their glows in patterns to court. In deep seas, creatures use blue-green lamps to lure, warn, and hide. Fluorescence is another soft magic. Corals and scorpions can absorb ultraviolet and re-emit visible light. Minerals in a cabinet under UV lamps explode into unexpected hues. Your laundry glows in clubs because optical brighteners turn invisible UV into visible blue to make whites look whiter. All of these spectacles follow the same simple rules: scattering, refraction, reflection, interference, and emission, rearranged by scale and setting. Knowing that doesn't blunt the wonder, it deepens it. The sky is a laboratory big enough for everyone, and once you know what to look for, halos near thin cirrus, sundogs on cold afternoons, coronas by the moon, faint glories when you stand above a cloud, you start to feel that light is not only illumination, but also conversation between the world and your eyes. Every star is a lighthouse whose beam carries more than brightness. It carries temperature, chemistry, motion, and distance coded into color and line. Hot objects glow with a spectrum that depends on temperature. Cooler stars lean red, hotter ones lean blue, and the peak shifts according to a simple rule. Hotter, peak at shorter wavelengths. But stars aren't smooth bulbs. Their atmospheres bite out thin absorption lines at precise colors, where atoms and ions grab passing photons as electrons hop between energy levels. Those dark notches, first mapped in detail in the sun and called Fraunhofer lines, are fingerprints for elements. Hydrogen's Balmer lines, sodium's twin near yellow, calcium's strong pair in the violet, iron's forest of marks. By comparing line patterns to lab references, astronomers read the chemical recipe of stars and gas clouds across impossible distances, finding common elements and odd enrichments that tell stories of past explosions. Motion imprints itself too. If a light source moves toward you, its waves bunch, shorter wavelengths, a blue shift. If it recedes, waves stretch, longer wavelengths, a red shift. A tiny periodic wobble in a star's lines can reveal an orbiting planet tugging it, a method called radial velocity. Another method watches a star's brightness dip slightly and regularly as a planet crosses its face, transits. During a transit, a minute fraction of starlight filters through the planet's thin atmosphere, where molecules leave faint extra absorption. With patient stacking, we can sniff for water vapor, methane, sodium, or carbon dioxide and sketch the hazy edge of an alien sky. On larger scales, the light of distant galaxies is stretched by the expansion of space itself. The farther they are, the redder they look, a pattern that first revealed the universe's growth. Massive clusters and galaxies can also bend light through gravity. Space curves around mass, and light follows those curves, so a distant galaxy can appear as a smear or an Einstein ring around a nearer mass. This gravitational lensing lets us weigh clusters, map dark matter that doesn't glow, and magnify faint background objects beyond telescope limits. Not all cosmic light is visible. Infrared pierces dusty nurseries where stars form, showing warm cocoons that visible light can't cross. Ultraviolet highlights hot young stars. X-rays flare from black hole disks and exploding stars. Radio waves trace cold hydrogen and molecular clouds. Stitching these bands together builds a multicolor portrait of processes from birth to death. The faint glow of the entire sky at microwave wavelengths, the cosmic microwave background, is cooled relic light from when the universe first became transparent. Tiny variations across it map seeds of structure that later grew into galaxies. Even nearer, Earth's own air glows at night with airglow, light from chemical reactions high above, a reminder that our atmosphere is an emitter as well as a filter. With these tools, we turn starlight into a library. We don't need to visit a star to learn that it spins, lines broaden, that magnetic fields warp its surface, Zeeman splitting, that heavy elements there were forged in older stars and scattered by supernovae, and that a small dark world may circle it on a gentle year we can mark from home. Light is the messenger that never tires. When we treat it with care, spreading it into spectra, timing it, comparing it, we hear the universe explaining itself in a patient, luminous whisper. Beyond seeing, light is a workhorse, a ruler, a scalpel, a courier, a tape measure for time and space. In fiber optics, a glass thread carries pulses of laser light that bounce inside by total internal reflection, racing through cities and under seas. One fiber can carry many conversations at once by using different colors, wavelength division multiplexing, and patterns. At the other end, a hair-sized photodiode catches whispers of light and decodes them back into voices, images, and data. In stores, barcodes and QR codes are simple optical puzzles. A red laser or LED scans black and white patterns. A sensor reads the reflected light, and software translates widths into numbers and links. The dot pattern you barely notice can store web addresses, tickets, or device setup details in a square your phone recognizes with a glance. Cars and mapping rigs use LiDAR, light detection and ranging, to emit short laser pulses and measure the time it takes to return from surfaces. Billions of these measurements build a 3D map of streets, trees, and buildings. In medicine, light peers gently inside. Endoscopes route white light in and images out through bundles of fibers or tiny cameras at the tip, letting doctors see and operate through small openings. pulse oximeters clip on a finger and shine red and infrared light through skin. Oxygenated and deoxygenated hemoglobin absorb these wavelengths differently, and a simple ratio estimates blood oxygen levels. In newborn care, phototherapy for jaundice uses blue light to change a pigment so the infant's body can excrete it more easily. Lasers cut or coagulate with precision because specific tissues absorb specific wavelengths strongly. Eye surgery uses cool ultraviolet to reshape a cornea. Green lasers target blood vessels. Infrared lasers seal leaks. Optical coherence tomography sends low-power light into tissue and measures tiny echoes from different depths, building cross-sectional images of retina layers or artery walls with micrometer detail, like ultrasound with light. In biology labs, fluorescence microscopy tags molecules with dyes that glow under specific colors. Filters pick out faint signals among background light. Newer super-resolution techniques beat the old diffraction limit by toggling tiny sets of molecules on and off and reconstructing positions statistically, revealing structures smaller than what traditional optics allow, all with careful control of light and chemistry. In factories, photolithography projects patterns onto light-sensitive coatings to build microchips. As features shrink, wavelengths shorten, and optics grow extraordinary, using deep ultraviolet and extreme control of vibration and air. Even timekeeping bows to light. Optical clocks trap atoms or ions and probe them with lasers tuned so precisely that the ticks are defined by light's oscillations, hundreds of trillions per second, yielding clocks so stable they would gain or lose less than a second over the age of the universe. These clocks help map gravity. Time runs a hair slower in stronger gravity and improved GPS. Around us, simpler uses abound. Projectors throw images with strong lamps and prisms. Remote controls flicker infrared. Traffic sensors watch lanes with invisible beams. Safety curtains around machines create grids of light that stop motion if broken. All rely on the same virtues. Light can be aimed, timed, split, counted, filtered, and turned into electricity cleanly. Because it moves fast and doesn't tug on what it measures, it's the gentlest probe we have for many jobs, from scanning a retina to counting atoms to mapping a cave without touching a stalactite. Learn how to ask light a question, and it answers with speed and grace. At small scales, light's graininess shows. A photon carries a packet of energy set by frequency. Even a weak lamp sends an intermittent drizzle of these quanta. When photons hit certain metals, they can kick electrons free, the photoelectric effect. Early experiments found that brighter light released more electrons, but that increasing brightness without raising frequency could not make them energetic enough to escape. Only bluer, higher frequency light could. This made sense when we accepted that energy comes in packets. The effect helped cement the quantum view. Today, light sensors, photodiodes, CMOS pixels, single photon avalanche diodes use these interactions to register single clicks, enabling low light imaging, time of flight ranging, and quantum experiments. Light also carries momentum, so it can push. The pressure from sunlight is tiny, but over time, and with big thin sails, it adds up. Experiments have flown solar sails that turn sunlight into a silent engine. Lasers can trap microscopic beads in optical tweezers, holding and moving them without touch. This won the Nobel for revealing forces in DNA and motors inside cells. Quantum strangeness climbs higher with entanglement, where two photons are created in a linked state so that measuring a property, like polarization, on one immediately tells you what you'll find on the other, no matter how far apart they are. This doesn't let messages outrun light. Nature protects causality, but it enables quantum cryptography, where any eavesdropping on a key exchange leaves detectable traces. Because single photons are fragile, these systems still face range and loss limits, but progress marches. Satellites have shared entangled pairs between ground stations, and fiber networks have carried quantum keys across cities. Light also threads the frontier of metamaterials and photonic crystals, engineered structures with features smaller than a wavelength that steer waves in ways nature seldom does. With them, designers can build ultra-thin metalenses that focus without bulky curves, mirrors that reflect only certain angles, and surfaces that swallow radar or glare. In chips, silicon photonics routes light alongside electronics, promising fast interconnects with lower heat. In everyday screens, quantum dots, tiny semiconductor crystals, convert blue LED light into very pure reds and greens, widening color gamuts while staying efficient. The quantum nature of light also shapes camera limits. At very low light, shot noise from the random arrival of photons sets a floor under which no amount of electronics can pull detail. You beat it only by gathering more light or more time. In spectroscopy, counting single photons lets instruments weigh faint signals from molecules with exquisite sensitivity. In astronomy, adaptive optics uses guide stars, real or laser-made, and fast mirrors to undo atmospheric blur, so telescopes can reach their diffraction limits on Earth. All these feats rest on the same deep picture. Light is both wave and particle, a ripple that can interfere with itself, and a messenger that arrives as discrete clicks. Matter is both particle and wave, with electrons forming standing patterns around nuclei that admit only certain energies. Where their rules meet, devices bloom. Cameras that see a few photons, networks that keep secrets with physics, sails that ride sunlight, lenses that are sheets, and sensors that time a beam's flight to the centimeter in a room or the meter on a hillside. Quantum is not only weird, it's useful, and most of the time it behaves gently enough to tuck into pockets. Let's bring light back to your room. If you remember a few friendly habits, everything you see and do will feel easier. First, tune layers. A warm, low ambient glow for comfort, task lights aimed where eyes work, and a few accents that make corners feel finished. In the evening, slide color temperature warmer and brightness lower so your body clock hears night. In the morning, give yourself honest daylight or bright cooler light for an hour to anchor your rhythm. Use high CRI bulbs where faces and food matter, and shield outdoor lights so they point down. Better for neighbors, birds, and stars. For screens, match brightness to the room, increase text size instead of squinting, and trim notifications. When you want sleep, let the room grow quiet in light as well as sound. If you're curious, turn your home into a tiny lab. A glass of water and a white wall make a prism. Shine sunlight or a phone flashlight through and watch colors spread. A bowl of milk with a drop of soap and food coloring shows surface tension drama in motion. A thin film of oil on water paints interference like a miniature sky. Stretch 2 pencils into a narrow slit. Shine a laser pointer through onto a wall. Mind safety. Never at eyes or shiny surfaces. And see diffraction stripes. Proof that light is a wave. On a sunny day after rain, stand with the sun at your back and look for the arc where rainbows form. Cup your hand to block glare and trace the constant radius. At night, put on polarized sunglasses and tilt your head at a laptop screen to feel polarization as brightness changes. On a lake at midday, rotate polarizers to erase glare and reveal the bottom. If you wear glasses, try placing a thin white paper just behind a lens edge and watch tiny coloured fringes along those high contrast edges, chromatic aberration, and appreciate the coatings that tame it. When you replace a bulb, test color rendering. Do tomatoes look appetizing or tired? When you walk at dusk, notice which streetlights feel harsh and which feel calm. Often the difference is glare control and warmth, not how many lumens they boast. Keep a sky checklist by the door. Thin halo around the sun means high ice crystals, sundogs on winter afternoons, moon coronas when mist rides a breeze, green rays rare at sea, glories if you hike above fog, air glow as a faint veil on very dark nights. And always practice gentle safety. Sunscreen and hats at altitude or snow, certified solar viewers for eclipses, no lasers near eyes, warm low light before bed, and a little shade for screens in bright rooms so you don't crank them to uncomfortable levels. Light is not only a subject for textbooks, it's a companion you can shape. With small choices, where to point a lamp, how to soften a window, when to dim, when to brighten, you write the mood of your home and the comfort of your eyes. Thank you for wandering through this patient tour of light and colour. May your room be softly lit, your screens kind, your sleep on schedule, and your curiosity awake just enough to notice a rainbow in a sprinkler, a halo around the moon, or the way morning slides across a wall. Thank you for listening, and good night.